Okay, so hello everyone. In the last lecture, that is BVLSI lecture number 20, we have started with module number 3, that is MOS circuit design styles, and we are focusing on unit number 3.1. And we have seen few examples of a static CMOS logic. So today we are going to explore that a little more. Okay, so last time we have left at the two input NAND gate realization using static CMOS logic. So this was the circuit which we have seen during the last lecture, and it contained two transistors, two NMOS transistors in series in the pull down network, whereas in the pull up network, those two transistors were in parallel with the inputs A and B. Okay, and yeah, the total transistor count over here was 4 for the two inputs. So for n input, inputs, you will require 2n transistors for static CMOS logic. Fine. And we have already seen the truth table. That is, whenever A and B both are 1, then only the output will be 0. Else for all other cases, the output Y will be 1. So let us consider one of the case. And we are assuming that whenever we apply 1 to a NMOS transistor, it will be on. If we apply a 0 to it, it will be off. If we apply 1 to a PMOS transistor, that will be off. And if you apply 0 to a PMOS transistor, that will be on. So over here, we are representing idle switches. So whenever a transistor is not on, we are representing by open circuit. So in the first case, when A and B both are logic 1, my both the NMOS transistors are on. And whereas my both the PMOS transistors are off. So my actually VDD is cut off from the output. So the only way for the output, we'll have is the output will be pulled down towards 0 volt by the transistors with NMOS transistors with the input A and B. Okay, and yeah, so that's why the output will be 0 in this case whenever A and B is 1 and 1. For the second case, when A is 1 and B is 0, your one of the NMOS transistor is off. That will disconnect the ground from the output. Now, in the pull-up network, the PMOS transistor with the input B will be on, so that the output node will be pulled up towards VDD. At the same time, the PMOS transistor with the input A will be off. But since it is a parallel part, we require only one part to conduct. So here the output is pulled up towards VDD via transistor, PMOS transistor with the input B. Now for the next case, when B is 1 and A is 0, the pull down network is disconnected because the NMOS transistor with the input A is open circuit. And over here, the PMOS transistor with the input A is on now, with the input B is off. So again, the output is pulled up towards VDD with the help of PMOS transistor with the input A. Now, if both A and B are 0, 0, so pull down network is completely gone and the output cannot go to 0, correct? But now, since A and B both are 0, 0, both your PMOS transistors are on and the output can be pulled up towards VDD via any of the transistors. Okay, so that's how internally this truth table works. So now let us verify this in LTspice. So already we have made the LTspice simulation ready for your reference. Okay, so now what we need to do is we need to simulate this. So here we have two transistors. Let me show it to you. It is similar to what we have done so far in the theory for building up the circuit. So this is your two input. This is your two input NAND gate. So here you can see very clearly the pull down network consists of transistors A and B. Remember, the body terminal of them are connected to the ground. And for the pull up network, we have two PMOS transistors connected in parallel. And their body terminal is connected to VDD. Now let us simulate this. So let me go on simulate and click on run. So you can divide the plane into 3 plots, to plot A, B and output. So the first plot will be A, the second one will be B, and the third one will be of the output. Now let us analyze that in detail. Okay, so these are the waveforms which we have got. We can see red color is A, blue is your B, and green is your output. So for the first case, when A is 1 and B is 0, output is 1. That is true for a NAND gate. NAND gate output is low only when A and B are 0. So in the second case over here, if you see A is 0, A is 1, B is 1, and the output is low. Okay. Now let's check next time when the output is low. So here again we have A as 1, B as 1. Again the output becomes low. Here it happens again, and here it happens for a very small duration. So here the A is on, B is on, and the output is low. So you have to be very careful when you apply the clock, A and B, okay, as a pulse. So it should be completely non-overlapping. If it is not, there will be some glitches at the output. So this is the waveforms and the verification for the 2-input NAND gate using LTspice. Now, let's proceed further. So similarly, you could implement a 2-input NOR gate, or we also call it as a NOR2, using static CMOS logic. So the expression F is given by A plus B bar, which can be written as A plus B bar into 1, or logic 1, plus A plus B into logic 0. Okay, so the first term over here, we can expand it. We can call it as A bar dot B bar into logic 1 plus A plus B into logic 0. So the first term over here in color, marked in blue, is my pull-up network. Okay, PMOS pull-up, which is expressed by A bar and B bar. And this is the pull-up network which connects logic 1 and the output. And the second one will be pull-down network, A plus B, expressed by A and B, and they are made up of only NMOS transistors. Now this pull-down network connects the logic 0 and the output. Fine. So here in the pull-up network, you have two PMOS transistors in series with the input A and B. And for the pull-down network, we have two transistors in parallel. So I guess this is what you were thinking. Yeah, you are in the right direction. So over here, we have the two NMOS transistors are in parallel with the input A and B. And over here in the pull-up network, we have exactly dual of it. We have two PMOS transistors in series. Okay. And the output is Y is equal to A plus B bar. Again, you can easily verify the truth table. The output will be 1 only when A and B are 0, 0. Okay. And here, since there are two inputs, it requires 2N transistors. So the transistor count over here is 4 for two inputs. Okay. So now let me move forward and let me come back to this slide. So here I have given some references for how to design a Boolean expression F. So you all can read it. It's the same thing which we have been doing from 1 or 2 examples. Now, let me implement F is equal to a Boolean expression, that is F is equal to A dot B plus C the whole bar using static CMOS logic. Okay. So let me play a video over here that will make the things very clear. So please listen to it and simultaneously do it in your books. Okay, hello everyone. Last time we have seen the implementation of a 2-input NAND gate using static CMOS logic. Okay, so let us proceed forward and let's implement a Boolean expression which is given by, let me take the color as black. So let us implement this expression. F is equal to A dot B plus C the whole bar. So this we have to implement using static CMOS logic. So the step number 1 is to expand this. So it can be written as A dot B plus C the whole bar into 1 plus A dot B plus C into 0. The 0 and 1 stands for logic 0 and 1. So the first network, the first expression over here, A dot B plus C bar will be my pull-up network, which will be consisting of only PMOS transistors. Okay, and the other expression is A dot B plus C. Okay, so this consists of pull-down network. Okay, this consists of pull-down network. Now let's make the circuit. So basically what we see over here is pull-up network will consist of your transistors, PMOS transistors. So your A will be in series with two transistors B plus C. So how the network will be? Let us try to implement. So we already know the general structure of static CMOS logic. We have a pull-up network when we have a pull-down network, and we have a pull-up network is connected to your VDD, and the pull-down network is connected to the output, and both of them are also connected to the inputs as well as the output. So let us start building the circuit for your pull. Let us first design the pull-down network. So pull-down network basically consists of your three transistors with the inputs, three NMOS transistors with the input A, B, and C. So first of all, let's implement B plus C. Okay, so that means two transistors will be in parallel. Okay, so this is my B and this is my C input. Let me write B and C, and this will be in series with transistor A. Okay, so let me join them like this, and this will be in series with transistor A, NMOS transistor A. So this is my transistor A. So this completes my pull down network. Now pull down network is connected to the ground. So this is my ground. Okay, now let's start with the pull up network. So for the pull up network, we have again the two transistors. Oh, we have to again, sorry, I haven't, again simplified this. So this can be again written as follows. Let me take a color pen over here, and I can represent this, open this using De Morgan's law, and it will be like A bar plus B bar into C bar. So you have to just open the, using the De Morgan's law, and you will get this expression. So this expression I will implement with the PMOS transistor, which will consist of a pull-up network. So I have two transistors, PMOS transistors in series, B and C. So let me do that over here quickly. So let me make two transistors in series, PMOS transistors. So one of them will be here. Okay. And another one will be, let's say, over here. So two PMOS transistors B and C are in series. Okay. And that is parallel with A bar. Okay. So A bar I will represent it like this. So this consists of my pull-up network. So let me take it a slightly upper so that I can fit it properly. Yeah. So this combination will represent the pull-up network. Let me show it to you. So this will be my A. Okay. So the pull-up network consists of A bar plus B bar into C bar. So that is what is representing, and if you join them together and you take out the terminal, that will give us the output, which is F is equal to A dot B plus C the whole bar. Okay, and we have to still connect the VDD over here. Okay, so this is the complete implementation for the following expressions: A dot B plus C the whole bar. Okay, this blue color is consisting of the pull-up transistors, and the red color consisting of the pull-down transistors. Remember again, the pull-down network consists of only NMOS transistors, and the pull-up network consists of only PMOS transistors. Now, what if the expression is, if we want the expression to be F is equal to, let me write over here, A dot B plus C. Only this much is given. Okay. So what we have to do over here is, we have to take double bar like this. Okay, and we have to implement this, and at the end what we need to do is, you implement this network, entire network you implement. So let me just show it to you. You implement this network, and at the output you connect an inverter. Okay, so at the output you might connect a CMOS inverter. So let us quickly draw a CMOS inverter like this. So you can easily connect a CMOS inverter at the output. And now this expression becomes, at the output becomes, F is equal to A dot B plus C double bar. Okay, because you have connected the inverter, which is same as A dot B plus C. So if you want output which is A dot B plus C, that's how you get it. So you make A dot B plus C the whole bar, and then you connect the inverter at the output. Okay. So that's how you make a Boolean expression implementation using static CMOS logic. Remember, whenever the pull down network is on, the output is connected to the ground, and whenever the pulled up network is on, the output is connected to the VDD. Fine. So that's it for this session. Okay, fine. So that's for the video. Now let's check this out um, in real time in LTspice. So here I have given the same thing in description. Okay. So I have also made the truth table ready. So we can verify some of the cases via the truth table, and we can also verify it in the LTspice simulation. So let me open that file. Let me close this. So that is Boolean number 1. Okay, so this is the expression f is equal to a dot b plus c the whole bar using static CMOS logic. If you see carefully over here, this is the same, network is the same. So here we have A, B, and C. Okay, and in the pull down network we have A over here and B and C. So you can see exactly symmetric, and then we can also check out the various waveforms. Fine, let me just keep it over here and let me expand this and let us simulate it now. So I've already taken care of other things. You have to just divide this into 4 planes. So let me take it as 1, A, B, C, and output. Okay, so that's why 4 planes. So let me maximize this. For the first, I will plot A. Next will be B. Next will be C. And the last one will be the output. Okay, now let's check this out with the help of the truth table. So let us check what is the first combination. First combination, the sequence will be A, B, and C, and the output. So it is 1, 0, 0. So 1, 0, 0. The output is 1 over here, and it should be 1 over here also, according to the truth table. Logic 1. Logic 1 means 5 volts. Second will be 1, 1, 0. So 1, 1, 0 will give you output as 0, and we are getting 0. So next will be 0, 1, 0. So 0, 1, 0 should give you 1, and it is 1 over here. Okay. Next will be 0, 0, 0. So 0, 0, 0, we have again the output as 1. Next will be 0, 1, 1. So 0, 1, 1 also the output is 1. Okay. So in this way, we can verify all the cases for the entire cycle. Okay. So all the cases, that there are around 8 cases for the inputs, 3 inputs. So 2 raised to 3, possible combinations are there. So we can check all the possible combinations in the output waveform. Okay. So this confirms that this circuit over here, which consisting of pull-up network and the pull-down network, will actually, work as which will be actually implementing A dot B plus C the whole bar using static CMOS logic. So the functionality of the circuit stands correct. Now let us go back to the PDF. Okay, so here the total transistors used will be, the inputs are 3, so the total transistors will be 2 into 3, that is 6. Okay, in this case, remember that here for the 2n cases, for the n input you require 2n transistors. That is only valid when there are no complementary inputs. Okay, that is only valid for no complementary inputs. We are plain simple A dot B plus C without any testing. And when we have to implement, let's say, this is second design methodology, wherein is the same technique. I'm not going to discuss it in detail. Pull down network is drawn with the same technique. Only thing is, pull up network is considered to be the dual of the pull down network. So I will give this for y'all for reading. So we are designing the pull up network with the dual of the pull down network, and it is actually true. Okay. So, but the end result will be same. So I'm not describing that in much details. Okay. Next, let's say I want to implement f is equal to A dot B plus C using static CMOS logic. Okay. So you just represent it in the form which we have done before. And at the end, you just connect the inverter. Okay. I'm sorry, here a bar will come, A dot B plus C, the whole bar. And here the bar should disappear. That is correct. Okay. So please take a note of it. And next, again, here the transistor count will be 6 plus 2. Okay, 6 transistors for the A dot B plus C the whole bar, and another 2 transistors for the CMOS inverter. Now, let us see that what will happen if we implement A complementary inputs. So it will be A bar dot B bar plus C bar, the whole bar. So here we have to generate the inverted input first, A bar, B bar, and C bar from the given inputs, A, B, and C. And then you define F using the inverted inputs. The remaining procedure remains the same. So here the pull-up network will be having A plus BC, and the pull-down network will be having A bar dot B bar plus C bar. Okay, so the implementation remains exactly the same. Only thing is inputs, all the inputs will be inverted. Okay, so complementary basically. So you have to generate them using three CMOS inverters. So the first one will generate A bar, second inverter will generate B bar, and the third inverter will generate C bar. So over here, the total transistor count will be 6 for the pull up and pull down, and 6 for the CMOS inverters. I hope that this design is clear to you. So whenever we have a inverted inputs, you have to connect a extra CMOS inverter to generate them. Okay. Now these are some principles of the dual logic. You can look at it. Okay. So the pull up and pull down networks work complementary. That's we have seen. If the pull down network is on, it connects the ground to the output, and if the pull up network is off, it disconnects the output from the VDD and vice versa. We have seen this. And if the two networks are dual, then they work complementary. Okay, so they work complementary. So now for your reference, you need to implement F is equal to A dot B using static CMOS logic, which is AND 2. So technique number 1 is you make F is equal to A dot B bar and then add the inverter at the output. Okay. Or the second technique is you take F is equal to A dot B bar, the whole bar, and then you can put A bar plus B bar, the whole bar, with two inverters to generate A bar and B bar. So you have technique number 1 and 2, you can choose any one. Generally, the first technique is preferred. Okay. Now the first one will be you have to implement F is equal to A plus B using static CMOS logic. That is OR 2. It is a 2-input OR gate. Okay. Next, implement F is equal to AB plus CD bar using static CMOS logic. And lastly, you implement F is equal to A plus B into C plus D, the whole bar, using static CMOS logic. So please try this out. And next lecture, if you have any doubt, you all can ask me this. Okay. Okay. So next we will see some background information on XOR and XNOR gate. So we have two input XOR gate. Okay. So two input XOR gate has the expression A bar dot B plus A B bar, and its truth table is given below. So whenever the inputs are same, the output is 0. Rest cases, the output is 1. In case of two input XNOR gate, this is two input XNOR gate. Okay. So you have the expression AB plus A bar B bar, which is here it is exactly complementary. When the inputs are same, the output is 1, and whenever the inputs are different, the output is 0. So basically, why study XOR and XNOR? Because XOR and XNOR operations provide the basis for the important systems, digital systems such as your adders, parity systems such as error correcting, detecting systems. So both XOR and XNOR use the input pair A and A bar, B and B bar. So thus the inverters are needed to generate A bar and B bar from the basic input A and B. Okay. So now the first task is to implement XOR gate using static CMOS logic. So let me share a video with you all regarding that. It will take a couple of seconds to load up. So kindly pay attention and do it in your books, the implementation of XOR gate using static CMOS logic. We're going to implement XOR gate using static CMOS logic. So the expression for the XOR gate is given by F is equal to A XOR B, or it can be written as A bar B plus A B bar. Now, normally using static CMOS logic, we have expressions in the following form, that is y is equal to x square. So in order to represent it that form, we can derive that f is equal to a bar b plus a b bar. We can prove it is equal to ab plus a bar b bar the whole bar. Also, the truth table for the XOR gate is given by whenever the two inputs A and B are equal, the output is 0. And whenever they are not equal, that is A is 0, B is 1, and A is 1, B is 0, that time the output is 1. Now let us prove the point where F is equal to AB plus A bar B bar, the whole bar is equal to AB bar plus A bar B. So we write this. The second step says we can apply the De Morgan's law. So what does the De Morgan's law say? It will be A dot B bar into A bar dot B bar the whole bar. Again we apply the De Morgan's theorem and we'll get A bar F is equal to A bar plus B bar into A plus B. Now if we get 4 terms, out of that the first term is A bar, which is actually 0. Second term is A bar B. Third term is A B bar, and the fourth term is B B bar. That is also equal to 0. So hence we arrive at the equation F is equal to A bar B plus A B bar, which is indeed equal to A B plus A bar B bar the whole bar. So let's start implementing this Boolean expression, which is of XOR gate. So the very first step is we can write it in the form F is equal to, A B plus A bar B bar the whole bar into 1 plus A B plus A bar B bar into 0. This 0 and 1 represents logic 0 and 1. So first term we can expand it a little more. It will be A bar plus B bar dot A plus B into logic 1. Second term will be as it is, AB plus A bar B bar into logic 0. Now, the first term over here represents the pull-up network. So this represents pull-up network. And the second term represents the pull-down network. Remember, the pull-up network consists of only PMOS transistors, and the pull-down network consists of only NMOS transistors. So this is my modified form of expression F. And I'm going to build this up. Let us first start with the pull-up network. So we have two transistors, A bar and B bar in parallel, that is PMOS, and the combination is in series with another two transistors, PMOS transistors with the input A and B. So we have to draw like this. So we have first two transistors in parallel with the input A and B bar, A bar and B bar, and this combination is in series with the two transistors again in parallel with the input A and B, like this, and we connect them together like this. So this represents the pull-up network. Now let's start building the pull-down network. So for the pull-down network, we have two transistors in series with input A and B. So let's draw that. So these are my two transistors with the input A and B in series, and that combination is in parallel with the two transistors A bar and B bar in series again. So here it will be A bar and B bar, and both of them are connected in parallel. So like this. So this is my pull-up network and this is my pull-down network. The blue color one is pull-up and the red color one is the pull-down. And now we connect the remaining of the circuitry. So this will be your VDD. We'll connect the pull-up and pull-down together. And this point is my output, which we call it as F, which we can call it as A XOR B. Fine. and below the pull down network is connected to the ground. So over here, this is my implementation of two input XOR gate. But is my design complete? Well, no. You have to generate A and A bar from A and B inputs. So to do that, we have to make a CMOS inverter. So let me quickly make two CMOS inverters and keep it ready. So that's the first one. And let me complete the second one also. So first one will be required to generate A and A bar, A bar, and the second one will be required to generate B bar. So if the first input over here is A, the output of the inverter will be A bar, and over here if it is B, it will be B bar. Okay, so that's how we implement a two input XOR gate using static CMOS logic. Now, how many total transistors are required over here? The total transistor count over here is 4 in the pull up, 4 in the pull down, so total 8. And also, you require 4 more transistors for the two CMOS inverters, so plus 4. Okay, so total 12 transistors are required to make a XOR gate using static CMOS logic. Okay, so that's all. So this was the implementation for the two input XOR gate. Now let's see that simulation in LTspice. So let me close this and let me open the Boolean number 2, which is two input XOR gate. Okay, so it contains a lot of transistors. So let me show you the implementation first. Okay, fine. So I want to show you all that it's in synchronous with the topics which we have studied. So here it is. The pull-up network consists of A and B with PMOS transistors A and B in parallel, and that combination is in series with A bar and B bar, and that's what we have shown over here. And here we have the output, that is Y or F, we can define it. And here we have in the pull down network, we have two transistors in series with the input A bar and B bar. And here again, that combination is in parallel with transistors A and B. Okay, so let's check out the output now. So this, I have already generated A bar and B bar from A and B using CMOS inverter, as you can see very clearly. Okay, and now let's check the output. So if I go to run, I have to divide it into 3 planes. One will be A, one will be B, and one will be output. So the first one will be A, VA, sorry, the input A. Next one will be B, and the last one will be my output V out in this case. Okay, so how does the XOR gate works? Whenever both the inputs are either 0 or either 1, the output is 0. So the first case we have input as A and B as 1 and 0. So the output is 1, obviously. In the second case, we have over here A and B as 1. So the output is 0. Next, we have A as 0 and B as 1. So the output is 1. Again, we have next case A and B as 0. So the output is 0. So in this way, we can go on and check all the possible combinations which was given in the truth table in the XOR gate. Okay, so that's how we can easily verify these things using LTspice very easily. Fine. So similarly, I want you all to try the implementation of the XNOR gate using static CMOS logic. Okay, so please try it out on your own. So I will share this PDF later. You all can check out for the solution later. Right now, let me jump to the overview summary of the static CMOS logic. So the static CMOS logic, the advantages are we have a rail-to-rail swing. That is, we have a full output voltage swing from VDD to VOL is equal to 0. There is no static power dissipation. Okay, there is absolutely no static power wastage over here. And here the output node is either connected to VDD or ground via low resistance part. You remember when any of the transistor is on, it offers very least resistance because the current starts flowing. That's why the word written over here, low resistance part. And with the static CMOS logic, we can implement any complex Boolean expression. The demerits are that it requires n input requires 2n transistors. Well, if you ask in case of XOR gate, we have only two inputs, but we require around, let's say, 4 plus 4, 12 transistors. But see, those things also contained complementary inputs. Okay? So whenever complementary inputs are involved, this relation won't hold true. Okay, in fact, it requires more than 2n transistors in this case. So the demerit of static CMOS logic as compared to other logics which will be studying is that it requires very large number of transistors to implement a Boolean expression or a logic gate. Some of the properties are that the voltage transfer characteristics is dependent upon the value of the input voltages. The propagation delay high to low and low to high are input data dependent. And here we have stronger pull-up means that output is strongly connected to VDD for a long time. That means your noise margin high will be higher and your logic 1 will be read easily as logic 1. That is the meaning of noise margin being high. And the stronger pull down means that the output is strongly connected to ground for a longer period of time. That means the noise margin low is low. So your logic 0 will be read correctly as logic 0. Okay, so these are the properties of your static CMOS logic. And with this, we end the topic of static CMOS logic design style. So next time we will start with pseudo NMOS logic. So until then, have a good day and thank you.